Students, our next topic is electric current. We know that flowing charges through a conductor constitute electric current. When charges flow through a conductor, then we say that current is flowing through the conductor. But how much current is flowing? For example, 1 ampere, 2 ampere. Therefore, quantitatively, electric current is defined as rate of flow of electric charge through any cross section of a conductor. A conductor have many cross section. For example, this is a cross section, or this is a cross section, or this may be a cross section, or this may be a cross section. Electric current is the rate of flow of charge through any cross section of the conductor. Suppose through a cross section or through any cross section a charge q is flowing in a time t, then electric current is total charge flown through a cross section upon time taken. Total charge flown through a cross section, let us take this cross section, this is q and time taken is t, then electric current will be q upon t. Often currents are not steady. Therefore, more generally, we can say that if delta Q is the net charge flowing through a cross section of the conductor in a particular direction, if delta Q is the net charge flowing through a cross section of the conductor in a particular direction in the time interval t, delta t. In time interval delta t mean between the time t and t plus delta t. Then current at time t will be delta q upon delta t. Delta t is the net charge flowing through the cross section of the conductor in a particular direction, and delta t is the time taken to flow that charge through a cross section. Then delta q upon delta t. As delta t is very small, then we can take limit delta t goes to 0. We can write this as dq upon dt. Therefore, dq upon dt is first derivative of charge with respect to time. Therefore, current through a conductor at any time is first derivative of charge with respect to time passing through a cross section of the conductor in a particular direction. Current through a conductor at any time is first derivative of charge with respect to time passing through a cross section of the conductor in a particular direction. Now, SI unit of electric current is ampere. This is also called practical unit. Now, I is equal to dq upon dt or I is equal to q upon t. When q is 1 and t is 1, then q is 1 coulomb and time is 1 second, then current will be 1 ampere. As I, electric current is q upon t. When q is 1 coulomb and time is 1 second, then I will be 1 ampere. Therefore, 1 ampere is 1 coulomb upon 1 second. Therefore, current through a conductor is said to be 1 ampere if 1 coulomb of charge is flowing through a cross section of the conductor per second. Current through a conductor is said to be 1 ampere if 1 coulomb of charge is flowing through a cross section of the conductor per second. Now, direction of current. Direction of current, we know that current carriers in metals are valence electrons which are negatively charged. When a potential difference is applied across the conductor AB with the help of cell, when a potential difference is applied across the ends of the conductor with a cell, then free electrons in the conductor, they move from end B to A, because here is positive potential, here is negative. Negative potential repel the negative electrons. Therefore, when some potential difference is applied across the ends of the conductor with the help of a cell, then electrons flow from negative end B to positive end A, because due to this positive electrode here is positive potential, due to this negative electrode here is negative potential. Therefore, due to negative potential, electrons move from B to A. Therefore, they are said to form a electronic current. Therefore, they are said to form a electronic current which flows from B to A, from lower potential to higher potential, because negative potential is lower and positive potential is higher. But normally water flows from higher level to lower level. Heat flows from higher temperature to lower temperature. Therefore, to maintain this convention, we define a conventional current which is equal and opposite to electronic current. We define conventional current which is equal and opposite to electronic current. It will flow from A to B, that is from higher potential to lower potential. In all our discussions, current will only mean conventional current which flow from positive end of electrode to negative end. Always current always means conventional current which flows from positive end of conductor to negative end of conductor, which moves from positive end to negative end in a closed circuit. Direction of current. As the current carriers in metals is valence electrons, when to a conductor a potential difference is applied with the help of cell, electrons will move from and B to A, that is from lower potential to higher potential. They constitute what is called electronic current. But we know that water always flow from higher level to lower level, heat flow from higher temperature to lower temperature. To maintain this convention, we define a conventional current which is equal and opposite to electronic current. This conventional current flows from positive end to negative end. In all our discussions, current will only mean conventional current which flow from positive end to negative end of circuit. Now current is a scalar quantity. Current is a scalar quantity. Though we know that electric current represents the direction of motion of positive charge, which is in a direction opposite to direction of motion of negative charge. Current represents the direction of motion of positive charge, but we take current as a scalar quantity because electric current does not follow laws of vector addition. Because electric current does not follow the laws of vector addition. The angle between the wires does not affect the total current in the circuit. The angle between the current carrying wires does not affect the total current in the circuit. For example, in this figure, AB is a conductor which is carrying current I0. At junction B, it splits into two branches carrying current I1 and I2. As the charge is conserved, therefore I0 is equal to I1 plus I2. This relation is not affected even when the angle between two conductors changes, when there is orienting or disorienting of conductors. This value do not change when there is orienting or disorienting of conductors. This relation remains valid in this situation and in this situation. Therefore, total current in the circuit do not change with the change in angle between the conductors. Therefore, current do not follow law of vector addition. Therefore, current is a scalar quantity.